This is Free Range Digital Design Foundation Modeling, Chapter 23, Lecture number 5. And we've been talking about finite state machines, developing some counters using finite state machines, and this is kind of a summary lecture. We're not going to do any example problems in this lecture. So this is our favorite model that we've been using over and over again. The idea is this is our digital circuit. This picture is actually from Chapter 1, where we have a bunch of digital modules under the control of something. What we're moving towards is controlling these modules with a state machine. Typically in real life you can also control them with a microcontroller. So these modules can be anything. What's listed here is sequential circuits, combinatorial circuits, and computer peripherals, which is once again idea for another course. This is the finite state machine model that we developed in the last 4 lectures. What we have here is 3 modules. So there's 2 decoders. We've got a next state decoder and an output decoder. Both of those are combinatorial modules because they are decoders. And also we have state registers, which are sequential circuit, of course, clocked. We have a little clock edge sitting there. We're not really marking that in the diagrams just to save space. The next state decoder essentially takes the current state and any external inputs, uses those values to determine the next state. And that's why they call it the next state decoder. Next state becomes the present state. Present state feeds back around and to the next state decoder for the next clock cycle. State registers are essentially just a register. We initially modeled them as flip-flops, but now we're just going to call them registers. They can have different features, but definitely it is a synchronous circuit. It is going to have a clock edge, and it's going to only be active on one of the clock edges, either a rising or falling edge. Now, so the output decoder, a little bit more complicated. We have 2 different types of outputs. So we have more outputs and we have Mealy outputs. So the more outputs are a function of state only, and that's what's indicated right here. Whereas the Mealy outputs are a function of both state, there's the state, and the external input. So this external input also decides what the output's going to be. The difference between these 2 is significant. Different types of outputs. It's probably the hardest thing about state machines, and particularly as it applies to the associated timing diagrams. But that's it. 3 modules, 2 decoders, registers, nothing complicated. More challenging stuff is using this circuit to control another circuit, which we haven't done yet. Certainly be doing that in some upcoming chapters. So the next set of slides is essentially a state diagram overview, and the issue here is it's just a quick overview of kind of summarizes what we've been doing in this chapter. The issue is it'll make more sense in later chapters when we're actually using state machines to control circuits. We're not quite there yet. State diagrams, it's a visual representation of the state machine, much better than staring at PSNS tables. The thing about state diagrams it's used in many fields of engineering and computer science as well. Many approaches to drawing state diagrams. I choose one approach and I stick to it. The biggest, most important thing here is you're trying to transfer information as quickly as possible, and you should use that as your guide. There are rules we are going to follow, but these rules are somewhat flexible in that if you can think of a better way to represent the state machine, you do it and you put a note there. You just make it clear to the reader. So that's the idea. If you go outside of the rules, document it. So the heart of the state diagram was the state bubble. Now the state bubble, it represents a state. State represents memory. Generally speaking, when we draw these things, we give it a self-commenting names. These states do represent what's being stored in the state registers, and it's not always apparent what exactly is being stored in the state registers. That's almost like a separate function that you don't really need to deal with at this point. Particularly what we're going to be doing is abstracting to a higher level than we generally don't really. States have a temporal delineation, for lack of a better word. So these state-to-state transitions are synchronized with a clock edge because the state is memory. The memory is held by a register. The register is a sequential circuit. Sequential circuits, generally speaking, are synchronous. Okay, so there's an issue of a present state and a next state. And the idea here is, where's the present state and the next state in this thing? All we have here is state. Generally speaking, when you're looking at a state, that is the present state, where the state following that is the next state. So essentially it's somewhat of a semantic argument as far as the present and next state goes. It's not overly apparent and or useful from a timing diagram. It's more of an issue when you're working with PSNS tables. State diagram essentially is used to indicate everything about the state machine, particularly changes in state and what causes those changes in states. And also, you'll see it later, it lists the output variables. Two types of synchronous transitions we'll actually run into an asynchronous one later. The two types of transitions are like a self loop, which essentially means that it stays in that given state, so whatever in the state registers does not change, or it goes to another state, and when it goes to another state, the values in those state registers necessarily change. So what we see here is at this transition, it goes from state 1 to state 1, that is representative of that self loop. And the second transition here, the state changes, that's representative of the arrow going from one state to the next state. State diagrams have state transitions, and something is going to determine when that transition takes place, or the conditions associated with that transition. We know what happens on a clock edge. The idea here is we always have to list the conditions associated with that transition next to the transition. And so this is what we're doing. We're listing the conditions that cause that transition to happen in the state diagram. Or sometimes these transitions are unconditional, which means we're just going to put a dash there. But if it has a condition, we have to be very explicit what that condition is and list it in the state diagram. Now there's two types of outputs. As you know, there's more outputs and there's Mealy outputs. The more outputs are a function of state only, so I can stick those outputs inside the state bubble. Now the Mealy outputs, they're essentially a function of the state as well as the external input. The external input decides the transition. So what I'm doing here, I'm taking these Mealy outputs and putting them next to the input conditions. Well, the input conditions decide the transition, so those input conditions are next to the transition. So it looks kind of confusing, but truly these outputs are associated with the conditions, the external input, and that's why we put it next to the external input. And the external inputs control how it's going to transition as well. So it's a little bit confusing. So the idea here is, one way to list this is these outputs are associated with an arrow, roughly speaking, and these outputs are associated with the state the arrow is coming from, and that's worth saying again. The outputs are associated with the state that the transition arrow is coming from. So this is a state diagram with both types of outputs. The Mealy output is next to the external input, which is next to the transition. The more outputs are actually stuffed in the state. No issue against having both Mealy and more type outputs in the same machine. State diagram gives four types of information: the states, which are the bubbles, the state transition, which are the arrows, and the inputs and the outputs. The outputs can be either Mealy or more type. More type outputs go in the state bubble. The Mealy type outputs are listed next to the external inputs, which are listed next to the transition arrow. So four types of information: states, transition, inputs, and outputs. Now state diagrams, they can be very complex, particularly when they have lots of inputs and lots of output. Okay, so generally on a per state level, the state diagrams are very simple. So generally in any given state, not all the inputs matter, not all the outputs matter. Generally speaking, when you're drawing these state diagrams, you only list what matters per given state. The idea here is if the input or output doesn't matter, you don't put it down there. And when you don't put it down there, that's okay. It's just interpreted as a don't care. So if you forget to put it down there and it matters, that's wrong. If you forget to put it down there and it's truly a don't care, that's okay. And in fact, that's encouraged, because if you have 10 inputs and 30 outputs, which is not that many for some circuits, it'd be really ugly if you listed all the inputs and outputs in a given state. You generally only list the inputs and outputs for a given state that matter. Everything else is a don't care. And lastly, we have our foundation model as well as our general model. And once again, so here's our general state machine model. It has 2 decoders and state registers, considered a sequential circuit because it has a sequential element in it, even though the 2 decoders are in fact combinatorial. This is our high-level model. This is our foundation model, which works very well with our other foundation models in that we are looking at the status of the circuit that this state machine is controlling. It looks at the status, decides what to do, and sends out control signals. And if you remember from the other foundation modules, essentially they are sending out status signals, which the state machine is reading, and they are inputting control signals, which are being output from the state machine. And we will see that quite a bit later as we work with state machines that are actually controlling circuits.